All right, so let's talk about what are integrated rate law. So we've already seen that there are three different order of the reactions that we're interested in: zero order, first order, and second order reactions. For a zero order reaction, rate is equal to rate constant times the concentration of the reactant to the power zero. So if we integrate this law over the period of time t, we get this particular law right here shown in red, and this is called the integrated rate law. Why is this important? Because this would allow us to actually determine the concentration of the reactant at a particular given time if we know what is the initial concentration and if we know what is the rate constant of that particular reaction. So essentially it will give us more information that we cannot get from the rate law by itself. So AT right here is the concentration of the reactant A at a given time t. A0 is the concentration of A at time 0, meaning initial concentration of A. K is our rate constant, and T is the time that we are talking about for this particular reaction. Here you see the integrated rate law for a first order reaction. Again, A0 is initial, AT is the final concentration at time t or the concentration at time t. In case of a second order reaction, rate law is rate equals K, A to the power 2. If we integrate this rate law over time period of t, it would give us this particular integrated rate law. Now, all these equations will always be provided to you in exams. What's important to know is which reaction is for which order of which equation belongs to which order of the reaction. Okay, that will not be told to you. So you should be able to figure out this is a zero order equation, this is an equation for first, this is for second. How can you remember that? My easy approach is that I try to remember, just memorize a little bit. So essentially, if you see concentration is written out normally in the equation, it's a zero order. When it changes to natural log, it's first order. And when it is reversed, it's second order. Okay. So zero order, normal, natural log, first order, and then reverse is the second order reaction. So if you say this a couple of times, it's going to sit in your head, right? So normal, zero order, first order is natural log, and for the second order, it's reversed. Okay. Now let's see what we can actually do with these if you know the integrated rate laws. So for instance, there is this question: at 1000 degrees Celsius, cyclobutane decomposes in a first order reaction with high rate constant of 87 second inverse to two molecules of ethylene C2H4. The initial C4H8 concentration is 2 molar. What is the concentration after 0.010 seconds? So let's try this question out. So what this is telling us, let's first write down. Let me clear the canvas. Okay, so now let's begin writing it out. First, let's write out what is given to us and what is being asked. Okay, so we're told that there is a reaction of C4H8 decomposing to form two molecules of C2H4. Right now, I'm not going to balance this reaction because I do not care. We'll see if we come to that point where we have to balance this equation. Okay, so it's telling us that this is a this is a first order reaction. That's just my abbreviation for a reaction. Okay, you might see it a lot, RXN, through this video. So this is a first order reaction. It is telling us that the rate constant, what is rate constant, is K. K is 87 second inverse, that's given to us. Then it tells us that the initial concentration of C4H8, so we remember how do you write that? C4H8 square bracket means concentration, initial means at time 0, is 2.00 molar. What is the concentration after 0.010 seconds? So this is time of the reaction, 0.010 seconds. Come on. Oh, there we go. 0.010 seconds. All right. The question is to determine what is C4H8 at time t. Okay. Do we know a relationship that kind of relates this? The concentrations and the rate constant in time? Yes, we know. For a first order reaction, this is our equation. Okay, ln A0 over AT equals KT. So do we know what is A0? Let's just put our equation in. So A0 is C4H8 at 0. Do we know that? Yes. C4H8 at T, do we know that? No. That's exactly what we want to figure out. right? Do we know K? Yes, we know K is given to us. Do we know time? Yes, time is given to us, right? So now it's fairly simple. We'll plug in everything into this equation and determine the concentration of C4H8. So let's plug in everything. 2 molar, 87 second inverse. Second, what's important, remember the units should match up. So this is in second inverse, this is in seconds. Perfect. So now we have to solve for this is equal to 0.87. Now, how do you remove natural log? Okay, to remove natural log, you essentially take anti-log of both the sides. When you take anti-log, whatever is on the other side essentially becomes small e to the power of that. And small e, if you plug into your calculators, it will be able to calculate. Okay, so if you take, if in order to remove natural log, you take everything becomes e to the power of that. And e to the power of natural log is essentially the same number. Okay, so natural log and e or this exponential essentially get cancelled. Okay, remember that you've done this before. You saw this in the previous video with nuclear chemistry as well. So it's going to apply, the same thing is going to apply right here. So if you solve for this, it will give you the concentration of C4H8 at time t, which is after 0.010 seconds. Right? Okay. Now moving on, here's, oh, we forgot to do, there's also a second part to this problem. Come on, can I go to the previous? Okay, there we go to the second part. The second part is asking part B. How long will it take for 70% of C4H8 to decompose? So now it's asking me for time that will take for 70% of C4H8 to decompose. What does that mean? That 70% of C4H8 is being used up. Okay. We only know in our equation of first order, the terms that go in are the concentration at time 0 and concentration at time t. Does this allow us to calculate what is the concentration at time 0 and concentration at time t? Tells us 70% of it is decomposed, meaning how much is left is 30%. So let's assume we began with, this is assuming C4H8 at time 0. Let's say since they're talking in percent, I'm going to take it as 100. Okay, so we began with 100 molar of C4H8 at time t. It's telling us that 70% of it has been used up. So what's left is 30%. So 30% of 100 is going to be 30 molar. So we began with this and we are left with this. Now we know these two numbers. We know K is given to us. We just have to solve for T. Can we do that? Same thing. We are going to plug in everything into this equation of first order. So assuming this is our first order reaction, we're going to plug in the numbers right here and solve for T. Okay, fairly simple. Okay, very straightforward. You just have to know which equation to use at what time. Okay, now again, it's important. It says right here 70% of C4H8 has decomposed. Okay, if it said that it has decomposed by 70%, it's actually the same thing. Okay, or it could say that it has decomposed to 70%. Okay, that means that only 30% of it has been used. Okay, so English in this case matters a lot. So make sure you understand the question very well. Right, moving on. There's another question for you guys. I'll let you guys try this on by yourself. It's again based on the same principle. We just have multiple examples to work on where you're going to use the integrated rate laws. Okay, so this is, let's just go over the question real quick. The rate constant for the second order reaction 2A changes to B is given to us. So rate constant meaning K is given to us. What is the original amount present if after 2 hours there is 0.35 molar available? So this is the time, 2 hours, and this is what's left at time t, which is after 2 hours. AT is given to us. The question is, what is A0? So again, everything's given to us except one of the parameters. So we just have to solve for that using the equation, which is for second order reaction, right? So I'm going to let you guys work on that. Here's the answer for it. Now this is radioactive decay, okay? The radioactive decay of a new atom occurs so that after 21 days, the original amount is reduced to 33%. What is the rate constant for the reaction in second inverse? Okay, this is not telling you if it's a first order, second order, what reaction it is. But what is it telling you? It's telling you this is a radioactive decay. Remember, we have done this in nuclear reactions. We looked through the kinetics of nuclear reactions before, right? A radioactive decay is a nuclear reaction. And what we saw in the kinetics of nuclear reaction is that all the nuclear reactions follow first order kinetics. Okay, if you do not remember that, I would advise please go back and look at the video for nuclear reactions. Okay, so this tells us that this is a first order reaction. Now, I'm not going to tell you anything else. What's given to you is time. What's told to you, original amount is given to you. It tells you original amount is reduced to 33%. Again, this is working in percentages, so you can kind of figure out if to begin with you had a certain amount, how much are you left with? Okay, the same kind of assumption that we made in our previous question, and then figure out what is the rate constant, right? So again, answers provided to you. You can feel free to pause the video right here, work on this question, and then compare your answers, right? And I'm going to move forward with the concepts so the video doesn't get too long. There you go. Okay. Now, this is a very important concept where we try to determine the graphical method to. Why is this important? You'll see later on. I'll give you certain examples. This is an approach that is used to experimentally determine what is the order of the reaction and what uh, order does the reaction follow. Is it a zero order, first order, second order, whatever is the order of the reaction, you can actually determine it experimentally, right? And how can we do that? So we saw that this is the equation for our zero order reaction, AT minus A0. Let me write that down. So concentration of our reactant at time t minus concentration of our reactant initially equals minus kT. Can I rearrange this equation? Let's rearrange this equation such that this is on the left side of the equal sign. So AT equals, what that means, AT equals minus KT plus A0, right? So what I did is I essentially added A0 on both the sides of the equal sign. This A0 got cancelled. I'm left with AT, and here we have a plus A0. Okay. So now that I have this equation, let me compare it to a linear equation. Okay, we have seen before what is a linear equation. Linear equation is essentially y equals mx plus b, correct? So if I now make a plot of y, which is at for me, okay, so if I make a plot of at versus time, so my y-axis is concentration of A over time, and x-axis is going to be time, just as you see right here on the PowerPoint. This is concentration of A over time, and this is time on the x-axis. So if I make this plot, is this comparable? Can I compare these equations to actually determine what would be my slope of the reaction? So in this case, my slope of the reaction is going to be minus k. So m is minus k, meaning slope is going to be minus k. What would be my y-intercept? Y-intercept is essentially b. So this right here is my y-intercept, which is a concentration of A at time 0, right? And as this, you can see the slope is negative. Therefore, in this case, you can see that the linear line is actually going is going down. Right? So this tells you that this is how a graph for a zero order reaction would look like. If we make a plot of AT versus time, this is how the graph would look like. It should look like a linear curve. If it's not linear, what that means is that it is not a zero order reaction. Okay, so experimentally, I can determine the concentration of my reactant over time, and I can make a record of the time. And then I'll essentially have a data table where I have concentration of my reactant and versus time. Then I can just plot this data, and if it gives me a straight line, that essentially means that this reaction, whatever I'm trying to study here in my experiment, is a zero order reaction. And if it does not follow a straight line, it means that it is not a zero order reaction, right? Now let's go quickly and look at this for the first order reaction. So this is my reaction, integrated rate law for a first order reaction. I can rearrange to give me this. So again, it's a natural log. Remember, natural log for first order. So if again I try to rearrange this equation so that I have concentration of A at a given time on y-axis on one side of the equal sign, and rest everything on the right side. So if I try to compare this, now y equals mx plus b. What changes is my y-axis, instead of being concentration of A at time t, it is natural log of concentration of A now. This is time, and this is again a straight line with a slope of negative k, where my y-intercept is now natural log of concentration of A at time 0. So if this reaction, first order reaction, should give me a straight line when I make a plot of natural log of A versus time. For a second order reaction, I can rearrange my integrated rate law to give me this particular equation. Again, this follows a linear line, y equals mx plus b, but now what is on my y-axis? It's actually inverse of the concentration of A. So the same rule still applies. If the concentration of A is normal, it's zero order. If it is natural log, be it graph, be it integrated rate law, it is going to be for first order, and for a second order reaction, it's going to be inverse, right? Now, interestingly, you can see that the slope in this case, which is m, is actually equal to plus k. Therefore, when you see this, the slope on this graph is positive. Okay, so the line is actually going straight up. The y-intercept here is 1 over concentration of A, initial concentration of A, right? Now, why is this important? Let's take an example. So this is like an experimental data that was collected for the decomposition reaction of N2O5. Over time, we measured the concentration of N2O5, and here is the data that you got. Now, how can you determine what is the reaction order? This is very similar to one of the experiments that we will be conducting in lab. So once we have the data collected, we know to determine the order of the reaction, we have to make 3 different plots, right? What 3 different plots can we make? So, okay, let me move. Okay, we can make 3 different plots. For instance, we can make a plot of concentration. I'm just going to write concentration of A versus time. We will make a plot of ln of A versus time. This is again concentration. Okay, or I can make a third plot of 1 over concentration of A versus time. And out of all of these plots, one of them is going to give me a straight line. And whichever gives me a straight line, I know that would be the order of reaction, because this is zero order, this is first order, and this is second order. Easy. So what we are going to do is, for this, we will calculate what is the natural log, we'll calculate what is 1 over the concentration, and we'll make 3 different plots. And here you can see the example. We have 3 different plots created. Out of these, I can tell that this plot right here is a straight line. It's following the linear law, which is for the natural log. And natural log I know is for first order reaction. So my answer is, this is a first order reaction, right? Easy. That's how you can graphically determine the order of reaction. But again, this is telling you the overall order of the reaction. It is not telling you the order of reaction with respect to each reactant. For that, we've already seen in the previous video how we can determine the order of reaction with respect to each reactant. Okay. All right, now moving on, let's talk about the another thing that's very important when you talk about reaction kinetics. One is speed of the reaction, the second is half-life of a reaction. What is half-life of a reaction? We have seen this term, we have heard this term before in nuclear chemistry. Half-life of a reaction is the amount of time that takes for in a reaction for half of the reactant to be used up or to be converted into product. Okay, so this half-life can be determined from the integrated rate law that we have. For a zero order reaction, the half-life is this. For a first order reaction, half-life is this. And for a second order reaction, half-life is this expression. Okay, so these are the 3 expressions. What you can see here, that as for a zero order reaction, half-life is directly proportional to concentration of A, meaning as the concentration of A would increase, half-life would also increase. So half-life is not a constant term, it depends on the concentration in a zero order reaction. But in a first order reaction, half-life is ln2 over k, meaning 0.693 over k. You do not see any concentration of reactant right here in this expression, meaning it is independent of the concentration of the reactant. So it does not depend on the initial concentration of the reactant that we are beginning with. It only depends on the decay constant. And we saw the same thing in radioactive decay. Radioactive decay or nuclear reactions do not depend on how much reactant are we beginning with. Now this is a second order reaction. You can see here half-life is inversely proportional to the initial concentration of A, meaning the more initial amount we have, the half-life is going to be lesser. Okay, so it's going to go faster. The reaction is going to go faster, which makes sense because this is based on the rate law again, right? Higher the order of the reaction for a second order reaction, we know the order of reaction is to the power 2. So faster the reaction, higher is the amount of the reactant, faster would be the reaction, meaning it's going to take lesser amount of time for half of it to be used up. Okay, so this is a summary table giving you all the information of chemical kinetics, combining the first video and this video right here. So you can go through this and it will give you all the information that we have discussed up until now. And if you do not understand any of this, please go back and look through the video again. This tells you what is the rate law, zero order, not dependent on concentration of reactant, first order to the power 1, second order to the power 2, right? These are the units of K, and we saw how to calculate those. This is the half-life. Again, all of these equations will be provided to you, but what is not going to be provided to you is which equation to use for what reaction, okay? This tells you what plot to make, what is integrated rate law, and what would be the slope and y-intercept, and what is the straight line going to be for which particular plot, okay? Perfect. So this is essentially just summarizing everything. Let's look at one of the quick questions for a first order reaction. What should be plotted in order to observe a linear relationship? For a first order reaction, again, we know zero order is normal concentration, first order is natural log concentration, second order is inverse concentration. So this is first order, meaning it's going to be natural log of the reactant versus time. There we go. That's your answer. Easy. Okay. Moving on. This is another question. For the following first order reaction of cyclopropane to propene, the rate constant is given to you. So what is the half-life of the reaction? So what is the information that's given to us in the question? It tells us that this is a first order reaction, which is great. Now it tells us that the rate constant, which is K, is 9.2 second inverse. The question is, what is half-life? Do we know a relationship for the first order reaction which relates K and half-life? Yes, we do, which is, oh, my bad, there we go. Ignore this bottom part. Look at this first part. T half is ln2 over K. So we just plug in the numbers and get our half-life, okay? So go back to part B. Part B is saying, how long does it take for the reaction of cyclopropane to reach 1/4 of its initial value? So how long does it take? So the question, part B, is asking for time. How long does it take for a concentration of cyclopropane to reach 1/4 of its initial value, meaning the initial concentration of our reactant, let's say if it is 1, the final concentration at time t is quarter of that, so 1/4. All right, so in that case, what's happening? You can either do it verbally. This is a first order reaction, right? So it will take how many? In first half life, it's going to be 1/2. In second half life, it's going to be 1/4, right? So this is essentially asking you, it's going to take 2 half lives. So we can either solve it in this way. If you can do this in your head, that's all right. 2 half lives, meaning 0.15 seconds. Okay, we calculated half life from the first part already. Otherwise, we can even go the longer route. Nobody's going to question you how you get the answer, right? So we know for the first order reaction, this is our integrated rate law. What is A0? We'll assume it's 1. What is AT? It's going to be 1/4 of 1, right? K is what the question is asking. K is given to us in the question, 9.2 second inverse, and the question is asking for how long will it take. So we plug in our numbers and we can solve for time, which is 0.15 seconds. Very same answer, right? You can use whichever approach works for you, right? Perfect. Moving on. Another very important topic that we touched a little bit in the first video is collision, right? We said that for a chemical reaction to occur, what's happening essentially is that all the reactants are colliding with each other, right? This is called the collision theory. What does the collision theory tell us? It tells us that all the particles must collide in order to react, okay? And an increase in the concentration of the reactant leads to larger number of collisions, and that's why it increases the rate of the reaction. More is the amount of reactants, more would be the collisions that happen, and therefore it would increase the rate of the reaction. Now, another important thing that we discussed was that not all the collisions are going to be effective enough to produce products. So the reacting species must colloid in a particular orientation that allows contact between the atoms such that they can actually break certain bonds and form new bonds, right? So it has to be in a particular orientation, and the other important factor is that it must occur with adequate energy. What does oh, what does adequate energy mean? So you might have already seen these reaction energy diagrams before, right? So we'll just go over these reaction energy diagrams. How do you read reaction energy diagrams? Let's look at, we'll give you some basic idea right here on the whiteboard, and then we'll go back to our diagrams right here, okay? So usually a reaction energy diagram is made with a plot of energy on the y-axis. So this is our potential energy of a reaction, okay? And on the x-axis, it's time or the reaction progress. Okay, so this is essentially over time what is happening in the reaction. So you always start to read these reaction diagrams from left to right. So in the beginning of a reaction, what will we have? We will only have the reactants, right? There wouldn't be any products being produced. The products are not going to be present. They will be present as the reaction makes further progress, okay? So to begin, let's say we have only reactants right here, and this is the energy of the reactants, the potential energy of the reactants at a given time. Okay, so let's say I'm talking about reaction of A is changing into B. So in the beginning, I will only have A. As the reaction progresses, these molecules of A will have to gain energy such that they can reach a very high energy state, which is called the transition state or the activation state, okay, where all these molecules are actually activated. So they are going to collide with each other with enough energy so that they can actually cross this barrier. Unless they are able to cross this barrier, they will not be converted into products. Okay. Now these are going to get converted. Once they cross this energy, they will go and get converted into products, which in this case is going to be B. So as the time is passing by, A is getting converted into B. Okay. What is this energy difference between the reactant and this is a transition state? Okay. Transition state is also called as the activated state. So these transition, sorry, not stated, it's state. So the transition state is also the activated state where all these molecules are very unstable. They're very high in energy. So it's very unstable and it does not stay here for a very long time. Okay. As soon as they reach the state, they're so unstable that they're converted into stable molecules, which is stable product right here. Okay. This energy difference between the transition state and the energy of the reactant, this is the energy of the reactant, right? This energy difference is called the activation energy. So until and unless the reactant molecules are able to gather enough energy to cross the barrier of activation energy, they will not be able to be converted into products. Okay, this is called activation energy. Okay, another difference in energy that you would see here is this is the energy of the reactants, right? And this is the energy of the products. So this difference right here in energy of reactants, energy of product is called delta H. Delta again means difference. H here stands for enthalpy of the reaction. So this is called the enthalpy of the reaction. You guys have probably heard that a reaction sometimes is endothermic or exothermic. What that means is if a reaction is absorbing energy, if it's absorbing, it's endothermic. If it's releasing energy, it's exothermic reaction. And who determines that? That is determined by enthalpy, change in enthalpy of a reaction. And what this enthalpy depends on, it depends on what is the energy of a reactant, what is the energy of product. So you can see right here, the reactants have lower energy and our products are higher in energy, meaning for this reaction to happen, A is going to absorb some of its energy, some of the reaction energy to be converted into B, right? So in this case, this reaction is going to be absorbing some energy, meaning this is an endothermic reaction, right? Let's go back to our energy diagram. So you can read from here, a particular reaction of NaOCl is getting converted to NO plus Cl2. In the beginning, we only have reactants. All the reactants, not all the reactants, again, they are going to collide with each other. Only the collisions which can actually reach this particular energy level, high activation energy, are going to be converted into products. Okay, so this energy difference between reactant and the transition state is the activation energy. What you see FWD here is forward reaction. So this is activation energy for forward reaction. This is the enthalpy difference. Again, reactants have less energy, products have more energy. So energy is actually being absorbed by the reaction. So it's endothermic. Looking at the second reaction where NO plus O3 is changing to NO2 plus O2, this is the energy of the reactants. They have to reach an activation state where then they can get converted into products. Here, the reactants have high energy, but the products are low in energy, meaning in this reaction, the energy is going to be released. Therefore, this reaction is an endothermic reaction, right? This is the activation energy of forward reaction. What you see right here is the activation energy of a reverse reaction, okay? REV. This essentially means that for a reverse of this reaction to happen, if there was a reverse of this reaction happening, then these products will have to gain this much energy first to get converted into uh, the reactants again. Okay, we'll talk about some reversible reactions later on in this course. For now, you don't have to worry about it, but essentially this is just telling you whichever direction a reaction is going, it's going to have some energy barrier to cross before it can get converted into products, right? Okay, so this is just another diagram explaining the same thing. We have reactants, activated state they have to reach before they can get converted into products. So you guys might have heard before that temperature can actually speed up a reaction, right? We saw that before in our first video, that when the temperature increases, the reaction tends to go faster. Why is that? Because when the temperature increases, the reactants have more energy now to begin with, right? So what is the effect that temperature has on the reaction? Let's take a look at that right here. So this is the effect of temperature on the distribution of collision energy. What that means is this is the collision energy, and for instance this is the reaction, how it looks like. This is a distribution of all the molecules present in a reaction at temperature T1, which is lower temperature. T2 is a higher temperature. Okay, so what's happening right here is at T1 you can see this is the distribution of the molecules. Different molecules have different energy. This is the activation energy that the molecules have to cross in order to form products. So you can see right here in purple shows you the fraction of molecules that actually have higher energy than the activation energy. So they can actually collide with each other with sufficient energy to form the products, right? What happens when the temperature is increased from T1 to T2? Now the overall energy of all these molecules is going to increase. So therefore you see a shift in the distribution of these molecules with respect to energy. Now the number of molecules it actually can surpass or cross this this energy barrier is this particular amount. So it's the fraction in red plus purple. So you can see overall the number of molecules that can collide with each other with higher enough energy than the activation energy is now more. And that is what causes the increase in temperature to increase the rate of the reaction, right? Okay, so this is just written it out for you in words. An increase in temperature causes an increase in kinetic energy of the particles. This leads to more frequent collision and the reaction rate increases. At a higher temperature, the fraction of collisions with sufficient energy equal to or greater than EA increases, and therefore the reaction rate increases. There's another factor that changes when temperature increases, and we'll see that later in this chapter. Okay, can we address or express this change in temperature uh, and the effect on reaction rate mathematically? Yes, it's given by Arrhenius equation, which states that K equals A e to the power minus EA over RT, where K is the rate constant. A is another constant, which is called as the frequency factor. So this frequency factor depends on two things. It depends on the collision frequency and it depends on the orientation at which this collision is happening, right? What is E? E is a constant term, exponential, right? EA is activation energy in joules per mole, R is again a constant, and T is temperature in Kelvin. So what you see here is that as the temperature increases, K is going to exponentially increase with that, right? You see this is an exponential relationship. It's not a linear relationship, it's an exponential relationship. So this is just showing you an example. So in this experiment, we have results or data for a reaction between ester and water. So these are our two reactants. You can see that the concentration of the reactants is same in all these four experimental conditions. What is changing is the temperature. And you can see that as temperature is increasing from experiment 1 to experiment 4, the rate of the reaction is also increasing. And why is that happening? The concentrations of the reactants are same. That is happening because our rate constant is increasing. So this is a graphical representation of that, and you can see that the rate constant is increasing exponentially with temperature, right? So now temperature changes two things. One is that increases the fraction of molecules that collide with each other with enough energy, right? So it increases the overall energy of the molecules in the system. Second thing it does is that it also increases the rate constant. So it's making these two changes, and that's why the rate of a reaction usually increases whenever temperature is increased. Okay. Moving on, this graphical representation of Arrhenius equation can also be done in a form of, oh, sorry, this equation of Arrhenius equation can also be represented in linear form. So again, if we take a natural log of all of this to remove the exponential, you will see it changes to this. Again, this can be represented as y equals mx plus b, y meaning ln k is going to be on our y-axis, x would be 1 over temperature on the x-axis. So the slope is going to be negative EA over R. Again, the slope is negative, therefore you see this line going down, and our y-intercept is equal to ln A. Okay, so if you have all this data provided to you, you can make a graphical representation and then make an estimation out of there. So if this reaction can also be written out in this form, ln K2 over K1. So here we are comparing two different decay rate constant at two different temperatures. So this is reaction 1 where rate constant is K1 at temperature T1, and this is reaction K2 where the reaction is being conducted at temperature T2. So you can see here by comparing these two reactions, we get this particular equation. So it's basically derived from this expression right here. Okay, and you can use this to solve questions like this. The decomposition of hydrogen iodide has rate constant of 9.51 times 10 raised to power negative 9 liter per mole second at 500 Kelvin and 1.10 times 10 raised to power negative 5 liter per mole second at 600 Kelvin. Find activation energy. So what's given to us is K1, which is right here, and T1 at temperature T1. This is K2 at temperature T2. K1 and T1 doesn't matter. Essentially what matters is this is the rate constant at a particular temperature. This is the rate constant at other temperature. So you can basically interchange 1 and 2. Okay, you can assume this is reaction 1, this is reaction 2, or vice versa. That doesn't matter. Just remember this is the K for this temperature. So if this is T1 for you, then this has to be K1, right? Find Ka. Do we know a relationship that relates this? Yes, we know this relationship. We know K2, K1, T2 and T1 is given to us. R is a constant. We already know that. Only unknown term right here is EA. So we plug in all the numbers and we solve for EA, right? So if you plug in everything, solve for it, it'll give you this answer. So the only idea here is that you should know all the equations will be provided to you. You should just know what to use when, and that depends on the question. So once you read the question, my advice is always write down what's given to you and what is the question asking. And then figure out, do we know a relationship that relates all of this? Okay. Moving on, let's talk about now orientation. We talked about two different things, right? For collision to be effective, there are two different things that's important. First thing is that they should collide with enough energy, which we already saw, right? Next thing is that they should be colliding with each other in appropriate orientation. Why is this orientation important? That factor is considered in Arrhenius equation by the factor called frequency factor. So frequency factor is given by Pz, where P is the orientation probability factor and Z is the collision frequency. So how many times are these molecules going to collide? That is the collision frequency. And in what orientation are they going to collide? That is being considered by P, right? The term P is specific for each reaction and is related to the structural complexity of the reactants. So how many atoms does it have and how are they going to collide, in which direction it should collide with the other reactant? That is all factored in by the factor of orientation probability, right? So that is collision theory. For instance, you can see right here, there are so many collisions happening between the molecules of NO and NO3, but only a particular orientation with a particular amount of energy is going to be effective enough to produce product. Rest all these collisions are just going to be ineffective. Now another term that you might have heard in chemical reactions is of a catalyst. A catalyst does what? A catalyst is something that speeds up a reaction, right? So if we are talking about speed, it has to be considered in reaction kinetics, right? So what is a catalyst? It's a substance that can speed up a reaction, but it is never consumed in the reaction. It is involved in the reaction, but it is never used up. So if you begin with, let's say, 5 moles of catalyst in the beginning of the reaction, at the end, you will end up with 5 moles of the catalyst. Again, it's never used up. But how does a catalyst speed up a reaction? A catalyst essentially just changes the pathway that a reaction takes. Okay, so let's say we are talking about a reaction of A plus B changing into product. So from this graph, you can see the red plot is the plot that shows the pathway for the reaction when it is uncatalyzed, meaning in absence of a catalyst. So A plus B has to collide with enough energy so that it can reach this particular transition state. And once it reaches this, it can go back to its product. Okay. But if a catalyst is present, what happens? It's shown by this curve in green. It changes the pathway that the reaction takes. So now instead of reaching for that high activation energy, it only has to reach for the activation energy, which is lower. So what does a catalyst do? A catalyst actually decreases the amount of activation energy that is needed for a reaction to occur. That's how it will speed up the reaction, because now the activation energy is less, so meaning the fraction of molecules that can actually reach this activation energy will be higher. So they reach this activation energy and they'll be converted into products. The important thing to notice here is that the energy of the reactants and the energy of the products remains the same. Only thing that changes is the activation energy of the reaction. Okay, so the thing that has changed here is the transition state and the pathway. It does not affect the energy of your initial reactants and the final products, meaning it does not change the enthalpy of the reaction, right? Activation energy the catalyst lowers the activation energy but does not affect the enthalpy of the reaction. Enthalpy is the difference in the energy of reactants and the products. That you can see right here is same for both the curves in red and green. Okay, so that's important. A catalyst does not change it, and a catalyst is not used up in the reaction. It only brings down the activation energy to speed your reaction up. Okay. All right. Now, another term that is very commonly used in chemistry is reaction mechanism. Okay. What are mechanisms? Mechanisms are essentially the steps in which a reaction occurs. So let's say we are talking about the simple reaction of A is changing to B, or actually let's just make this reaction a little bit complicated. Okay. So let's say, okay, let's move this here. Cleaner, okay? Let's say we're talking about a reaction of A. Let's change the color. Okay, we are talking about a reaction of A plus B is changing into C plus D, okay? This is our overall reaction. When we talk about a balanced equation, we are talking about the overall reaction. This is the complete reaction that is happening. What mechanism tells us, okay, so there we go. What mechanism essentially tells us is that this reaction is not usually straightforward. It is not happening in one step. It does not mean that A plus B are going to react with each other to straight away give us C and D. It could be that A plus B will react with each other to first form E. Then E might react with something else like F to, or B, another molecule of B to give us F. Then F might react with another molecule of A to give us, I don't know, G. Then G might react with G itself to actually now go and produce C plus D. Okay, so the overall reaction that you see right here is A plus B changes to C plus D. Okay, but it might be going through multiple steps. Okay, to give you this overall reaction. And each of these steps is called an elementary step of that particular reaction. Why is this important? Because each elementary step determines the rate of reaction or the order of reaction. Not each elementary step, but one of these elementary or a couple of these elementary steps are going to determine that. And how? Let's look at that. Okay. So if you guys remember, we have discussed this before, that whenever we talk about rate law, let's say A plus B is changing to C plus D, we say rate equals K concentration of A square times B. Okay, I'm telling you this is my reaction and this is a rate law for this particular reaction. What is the difference? What's the important thing that we talked about for in the first video? The most important thing is that the order of this reaction with respect to a particular reactant is not equal to the stoichiometric coefficient for the overall reaction, right? So you can see here the order of reaction with respect to A is 2, but the stoichiometric coefficient of A in this overall reaction is 1. So it does not depend on the stoichiometric coefficient of your reactants in the overall reaction. What does it depend on? This rate law is coming from the elementary steps. Okay, So let's take a look at some of the elementary steps right here. For instance, let's say if this is my elementary step, A is changing into product. How many molecules of the reactants are involved in this reaction? Only one molecule of A at a time. Therefore, this reaction, in case of molecularity, is called a unimolecular reaction because there's only one molecule involved. What is the rate law for this reaction? Rate equals K, A to the power 1. Why? Because in this case, I'm going to use the rate law based on the stoichiometric coefficient. Okay, only when it's telling you that this is an elementary reaction. Okay, for instance, if I tell you this is my elementary reaction, 2A changing into product, can you predict what is the rate law? Yes, you're telling me this is an elementary reaction, meaning this is the actual mechanism. This is one of the elementary reaction that's happening. This is going to determine, if this is going to determine the rate law, it's going to be rate equals K, A to the power 2. Where am I getting the 2 from? From the stoichiometric coefficient. Now, if I just tell you this is my particular reaction, can you predict me what is the rate law? My answer would be no, I cannot tell you because you're telling me this is a reaction, but you're not telling me if this is the elementary reaction or not. If this is an elementary step, only then you can predict the rate law, right? Perfect. So if that makes sense, what is the molecularity of this particular reaction? It's 2. Why? Because there are two molecules of A that are reacting with each other to produce product. Now look at the third reaction. A plus B is changing into product. What is the molecularity here? How many reactant molecules do we have? We have one of A, one of B, meaning a total of 2. So this is also a bimolecular reaction. What is the rate law? Rate is going to be K, concentration of A times concentration of B, all raised to power 1. Okay. What is the order with respect to A? 1. Where did I get that number from? Stoichiometric coefficient. What is the order with respect to B? 1. Stoichiometric coefficient. What is the overall order of the reaction? 1 plus 1, meaning 2, right? Only because this is a elementary step. You cannot predict the rate law until you are told that this is an elementary step. Remember that, okay? Next example is 2A plus B changing to product. What is the molecularity? 2 plus 1, 3. So in this case, if 3 molecules are involved, it's called thermolecular reaction. What is the rate law? Rate equals K, A squared, concentration of B to the power 1. Okay. So what is the overall order of this reaction? 3, right? What this means that in case of elementary steps, whatever is the molecularity of the reaction is same as the order of the reaction, overall order of the reaction. What's the overall order for reaction 1? 1. Unimolecular, 1. What is the order here? 2. Bimolecular, 2. What is the overall order for third one? 1 plus 1, 2. Bimolecular. What is the overall order for this elementary? 2 plus 1, 3. Thermolecular, meaning molecularity of 3. All right. So only in case of elementary step, you can tell me what is the rate law. You can tell me what is the overall order of the reaction based on its molecularity, right? Okay. Moving on, let's talk about a rate determining step. What is a rate determining step? Now, how did I get this? Okay. For instance, let's look at this example, back to our example, A plus B changing to C plus D. My rate is K equals A squared times B. Okay. Overall order is 2 plus 1, 3. How did I come up with this rate law? Experimentally, yes, right? But can I explain this by mechanism of the reaction? Yes. Now let's take an example. Let's say we are grilling cheese sandwiches, okay? So to make sandwiches, we have like 4 people trying to make one sandwich at a time. One person is putting one loaf of bread. The second person is placing a cheese slice on that loaf of bread. The third person is placing the second loaf of bread. And the last person is actually grilling the sandwich, right? So there is a step that's involved. So just like how in chemical reaction, multiple steps are involved, here we have multiple people involved in the reaction, okay, of creating our grilled cheese sandwich. So let's say the first person is working really fast, the fastest that they can. The second person is working really fast as well. They're placing the cheese slices as fast as the first loaf comes in. But the third person, he is taking his own time in placing the second loaf of bread on to create that sandwich. The fourth person, again very fast. As soon as he receives a sandwich, he's trying to grill it. He's going the fastest that he can. So who is going to determine how fast I can get a grilled cheese sandwich on my plate? Is it the first person? He's going the fastest that he can. Second person, same thing. Third person, on the other hand, who is going the slowest out of all, is going to determine how long it's going to take for me to get my sandwich served. Is that correct? Because If he tries to go fast, I'll get my sandwich out fast. But if he tries to go slower, I'll get my sandwich slower. So who is determining the rate at which I receive my sandwich? The person who is slow, right? That makes sense. So same thing happens in a chemical reaction. There are multiple steps that are involved in a chemical reaction, right? Multiple elementary steps, each called the reaction mechanism steps, right? Out of these steps, some reactions are going fast, some are going really slow. So who is going to determine what will be the rate of my overall reaction? The step that is going the slowest, right? So the slowest step in a reaction is the rate determining or the rate limiting step. So this rate law that we derive or that we get for a particular reaction is actually the rate or the slowest step of the reaction. Okay. For instance, let's take a chemical actual example of a chemical reaction where we have NO2. So this is the reaction. NO2 plus CO changes to NO plus CO2. These are the reaction mechanisms that are told to us. Okay. So let's write down the first step. NO2 plus NO2 is changing to NO3 plus NO, right? It's telling us this is one of the steps. This is the slow step, meaning this is the rate determining step. And it's telling us this is a mechanism, so this is one of the elementary steps. So based on this reaction, this information, can I determine what is the rate law for this reaction? Yes. Rate law for this is going to be rate equals K times the concentration of reactant, which is NO2 and NO2. So we have two molecules of NO2 here, so it's going to be NO2 squared, right? Is that correct? This is a rate law for this elementary step. Now the second elementary step is NO3 plus CO is changing to NO2 plus CO2. It's telling us this is a fast step. What is the rate of this particular elementary step? What is the rate law? It's going to be rate equals K NO3 to the power 1 times CO to the power 1. How can I predict it? Why? Because it's telling me this is an elementary step. So I can just go by the stoichiometric coefficients of my reactants. Perfect. So now I have two rate laws. How can we get the overall reaction from here? Let's add up these reactions. So NO2, I have one NO2 on the reactant side. I have one NO2 on the product side. So it's being used up, it's being produced, meaning it's going to cancel each other out, right? Then I have one reactant NO2. Do I see another NO2 here on the product side? I don't. So this is one of my reactants. Then I see this reactant right here, NO3. NO3, do I see an NO3 in the product side? Yes. So here, this is being reacted, this is being produced. So essentially they cancel each other out because here it's being produced, but again, it's being used up, right? So it cancels. Next, I have another reactant, which is CO. Do I see a CO in the product side or in the reactant side? I do not, meaning this will be my other reactant, is changing to product NO. Do I see any of it here? I do not, so it comes in my overall reaction. Do I see anywhere else CO2? I do not, so it comes in my overall reaction. You can see here this reaction, overall reaction matches with my balanced equation. That's how from the mechanism steps you can actually determine what is your overall reaction. So my overall reaction is same, but now I know this is the mechanism and these are the rate laws for each of these steps. Now, if the question is asking what is the overall rate of this reaction or rate law, can you tell me? Yes. If you're giving me the information, these are the elementary step, and you're telling me that the first reaction is actually the slow reaction, then that means this is going to be my rate determining step. So my rate of the overall reaction is going to be whatever is the rate for the rate determining step. So overall reaction rate is rate equals K NO2 squared. So again, you can see this is not same as the stoichiometric coefficient of overall reaction, and CO is not mentioned in this rate law. Why? Because it is not dependent on the concentration of CO, the rate. Okay, does that make sense? So that's how you can actually determine what is the rate law for the reaction. It depends on the rate limiting step. So you figure out what are the different mechanism steps, what is the rate law for each step, and whichever one is the slowest step is actually going to determine the rate law for your reaction. Okay. Okay, so this is one of the questions for you to work on. So the following elementary steps are proposed for a chemical reaction mechanism. This is the mechanism. Cl2 is changing to 2Cl. Cl plus CHCl3 changes to HCl, CCl3, Cl plus CCl3 changes to CCl4. It's telling us that the second reaction is the slowest one. So we know this is the rate determining step to begin with. Write the balance equation for the overall reaction. How will we write the balance equation? We are going to cancel the reactant, which is also present on the product side. And if we have reactants that are present on both the sides, that will get cancelled. And if we have reactant that is involved in multiple reaction, we'll add those up. So let's quickly write this down. Don't want to take too much time. So we have Cl2. So actually, can I move this up? Okay. So to begin with, we have Cl2 gas is changing to 2Cl. Cl plus CHCl3 is changing to HCl and CCl3. The third is where Cl plus CCl3 is changing to CCl4. So if you're doing it on your own by yourself, I would really advise to put all the phases of these reactants and products, okay? Just how it's written. It's gas, 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 because you can only cancel out gases with gases, okay? So remember to write that down. I'm just trying to make this video shortest as possible, okay? So these are all our reactants and product. The question is overall balanced equation, so that means I'll have to do some canceling out here. So let's start with our first reactant, Cl2. Do I see Cl2 somewhere else? In any of these, I do not. So that is going to go straight into my overall reaction. Cl, do I see any Cl right here? Yes, there is a Cl here. So one Cl will cancel one of these Cl molecules. I also see a Cl right here. So that Cl will cancel the other Cl right here. So I do not need any Cl in my overall reaction. Next is CHCl3. Do I see a CHCl3 anywhere in this reaction? Anywhere else? I do not. So I'll go back. This will come in my reactants, CHCl3. Now let's see, next reactant that I see, I like to first cover up all the reactants, then I move on to the product side. So next reactant we have is CCl3. Do we see any CCl3 anywhere else? Right here. This is the product. This is a reactant. So it's being produced and it's being used up, meaning I will cancel those out. So I'll not have a CCl3 in my overall reaction. Now let's move on to product. So I've already figured out what are my reactant side. Let's move on to products. Product, HCl. Is there anywhere else? It's not. So it goes into my overall reaction. Next is CCl4. So CCl4 gas. Perfect. So now I have a balanced equation for overall reaction. Next part, determine the molecularity of each step. First reaction, only one molecule involved. So the molecularity here is 1. Perfect. Let's make it bigger. Okay, there we go. So what is the molecularity? For the first step, it's 1. Second step, I have 1 plus 1, 2 molecules reacting, so it's a bimolecular reaction. And that's how you're going to answer it. You're not going to write 1 and 2. You're going to tell me the molecularity as bimolecular reaction, okay? The third one, 1 plus 1, again 2. So this is also 2 molecules reacting, so it's a bimolecular reaction as well. That's what your answer will be. Write the rate law for each step. Okay, so rate law for this is going to be rate equals K. It's dependent on the concentration of its reactant, which is Cl2 to the power of 1. Why? Because the stoichiometric coefficient is 1. Rate law for this reaction, I'm going to write right here, might not fit. We'll try rate equals K Cl to the power 1, CH Cl3 to the power 1. Okay, rate for this reaction, we'll write right here, is going to be rate equals K reactant first to the power 1, reactant second to the power 1, again from the stoichiometric coefficients. Okay, write the rate law for overall reaction. What would be the rate law for overall reaction? Is it going to be added, all of this? No, it will be same as the rate law for the slowest step, which is our rate determining step, which is number 2. So this is going to be the answer for my rate law for overall reaction. Right, I hope this makes sense to everyone. Right, there's another question for you to work on. This is the reaction mechanism that has been proposed for decomposition of H2O2. One is a slow step, one is a fast step. The question is, what is the expected